Hi everyone, thank you for attending on short notice as well, as I know the comms came out a bit late this time for this lecture. We've got Rory Clarkson, who is an Associate Fellow for Engine Environmental Protection, an Honorary Professor of Geology at the University of Manchester, and also has an MBE. He's the world-leading expert on the effects of atmospheric agents such as volcanic ash, mineral dust, ice crystals and salts on the GT, and we'll be talking a bit more about that in today's lecture. So thanks for joining.
Yeah, well, welcome. It is a small audience, but it's a high quality one. I'm absolutely sure of that. I walk around and use my arms a bit, but do signal if you can't hear or lose track of where I am. So that's the title. Engine environmental protection often confuses people. They think it's about us protecting the environment. It's not. It's the other way around. This is about the climate. The environment is changing. The weather at the moment is demonstrates that. But the environment is biting back. The aircraft engines do emit carbon and other things that can lead to increased global temperatures, and you'll see in a minute reduced global temperatures. But that is having an impact on the engines. So I'll talk you through the agents or things in the atmosphere other than oxygen and nitrogen that can cause engine problems, and there are quite a few. And I'll talk a little bit about myself. Now, this pack is based on presentation material I fairly regularly present to students at universities and non-engineering people. It's reasonably engineering-y, but it's I try and keep it relatively 101 level, introductory level. I do include the mug shot of myself, but that's a few years old. And I've got some post-nominals, but tend not to advertise them too much. It's very nice to have been honoured with one or two of them. That's my career history, which is reasonably unusual, and I think about to achieve a degree of symmetry, and we'll talk about that at the end. So I am of an age, I left school in the early 80s with the intention of becoming a geologist. I'd done geology A-level and spent a year at Manchester University doing geology and found it incredibly boring. It was descriptive, and after a year I thought, no, I like to do something a bit more interesting. I hadn't done physics A-level, I'd done maths and chemistry. So I left not knowing what to do. Despite my accent, from the age of 11, I grew up in Cumbria, a place called Cockermouth. And local to Cockermouth was Sellafield. So I got a job there at British Nuclear Fuels. Very interesting 4 years. More interesting than I'd anticipated, because I stayed for 4 years. But at the end of that, by which time I was 24, that I originally had thoughts of doing physics, but by then I'd realised actually what I wanted to be was an engineer, and I left and took up a place doing a Bachelor of Engineering, mechanical engineering, and 4 years later, still in by then my late 20s, decided I had a good degree, I'd go and see if I could do a PhD, and cars were interesting to me at the time, and the opportunity to go to Coventry and do a PhD on catalytic converters with Jaguar Cars and Coventry University was one I wasn't going to miss. I did that, and it was very much computational fluid dynamics based. So from there, after graduating, by which time I had actually met my future wife, we moved to London. I worked for the company that is now owned by Siemens that produced the Star CCM Plus code. We got married and had a family, decided to move out of London. I knew this part of the world, so Rolls-Royce were looking, so I joined Rolls-Royce. And you can see in blue my Rolls-Royce career, which I came in as a pure specialist, but after a while, going up the promotion route, acquired more and more. I ended up as a team leader by accident, because the team leader was off long-term ill and they needed somebody to stand in. So I said I would do it. Before you know it, you're stuck. You end up getting promotion through management, and eventually ended up going back to being a pure technical specialist. But the last 15 years, in 2010, which was an interesting year for aviation for a number of reasons, I've been purely involved in this topic of engine environmental protection. So this is what I take people through, a bit of background on what are the harsh agents or elements of the the atmosphere that cause problems for aircraft engines. These was on how they affect engines, and then what we, Engine Environmental Protection, or EEPs we call ourselves, are doing to help the company and the industry mitigate the problems they cause, right? Whether people realize it or not, we almost pretty much exclusive, not quite, today still design engines for an atmosphere that doesn't exist. The international standard atmosphere is a thermodynamic ideal. You talk to pilots, they've never flown in it. You never get it. We might think about on a hot day what it might look like, but that's a simple graph of the international standard atmosphere. We do design it engines with things like birds and lightning and HIRF, high intensity radiative field, space weather actually, right, rays that come from space. We do have design rules for that, but there's lots of other things in the environment which we don't generally design to. One thing I mentioned a bit before we started, preamble to one or two in the room, climate change. Climate change is having an impact, and it's changed. Even if you take the thermodynamic ideal of the ISA, International Standard Atmosphere, it's no longer applicable, because we know, you can see outside, the lower part of the troposphere is warming up. What people may not realize, the stratosphere and the upper reaches of the troposphere are cooling down, and it's to do with the carbon dioxide in it. I understand why where we are in the troposphere is getting hot, because of the infrared radiation not being able to escape, so we're warming. But apparently, I need to read up more on the science, when you get to the top of the troposphere but also into the stratosphere, carbon dioxide works the other way. It actually increases the radiative heat loss out into space. So the stratosphere is cooling down, and the top of the troposphere as well. Cruise altitudes are getting colder. We think, oh, that's interesting. Is that a problem? Well, because we design aircraft to operate at a Mach number, because we're all very clever engineers, we will know Mach number is proportional to the square root of the temperature. So if the temperature of the air you're flying in drops and you're flying at a fixed Mach number, your ground speed reduces. And it's depending on climate, local weather conditions, it's taking up to 20 minutes longer to get from Europe to America, because at cruise altitudes across the top of the Atlantic, it's cold enough. It's becoming cold. The strength of the jet stream the other way is helping, but sometimes the jet stream's not very strong like it is at the moment, and you don't get that advantage. But what the EEP team really focus on is things like this, and this is the presence of water in the atmosphere is what essentially makes the ISA day, or the ISA International Standard Atmosphere, ideal and not real, because water changes the thermodynamic profile as you go up. Water in itself causes problems, and these are the main agents that we worry about, and we'll talk through how they affect engines. So freezing fog, freezing cloud, so that's tiny water droplets at 4,000 or 5,000 feet up to 20,000 feet kind of altitude. You go higher, the water will be ice crystals, and that causes problems, or cumulonimbus clouds. But at the bottom of those, you get a lot of rain and hail. This one's lightning and things. So they are problematic. In recent years, certainly since 2010, the world woke up to the reality. People knew about it, but it was a select few. Volcanic ash is a problem for aviation, and volcanic sulfur is as well. Pollution from, we call it anthropogenic activities, so human activities in terms of transport, cars, ships, aircraft, but also production of petrochemicals, burning of coal, things like that, but corrosive gases and aerosols in the atmosphere, and mineral dust, often called sand or dirt. The Americans like to call it dirt, but if you're being scientific about it, it's technically mineral dust. Most of the particulates that cause problems are less than 1/10 of a millimeter, and at that size, it's dust. It's not. Talk more. So this is a little question. I won't potentially embarrass anyone in the room. That why does the troposphere get colder as you go higher in altitude? And I was told this at school and even part of my degree, but I never did quite stack up. It was a complete story. As you go up, the air pressure drops, therefore the temperature drops. If that was simply the explanation, why would the stratosphere get hotter? The pressure's dropping, but it's getting warmer. There is a, I'm looking at the faces, interesting. I'm very confident we all know the science to explain why the troposphere gets cold as you go higher. And it's to do with the tropos means turning, the churning of the air. And that's the clues in there. And it's to do with the adiabatic expansion or near adiabatic expansion of an ideal gas. So you've got the air down at the ground, which is compressed and at a high pressure and therefore small volume. As it rises under a buoyancy effect or convection, it'll expand. And if you expand a gas ideally adiabatically, it will get cold. Conversely, when it turns at the top and comes down, which is what's happening here, we're in high pressure, the air's falling and getting compressed, it gets hot. And it's that turning that is the reason why the troposphere gets cold. And as climate change progresses, the troposphere is getting higher because there's more energy near the ground to drive the air higher. And that also means as it gets higher, the air will expand more and get colder. So the troposphere above the equator currently is about -80 Celsius. Above us, it's about -50. And it's because the troposphere above the equator is about 50,000 feet. Here, it's about 30,000 feet. And it's to do with that. Simple thermodynamics, but that's never explained like that at school. But we can all understand that. Anyway, that gives you an idea of the kind of science we as EEP engineers, and most of us are engineers, need to understand. So let's think about the effect of this temperature on water. And another surprising piece of information for many people is water doesn't freeze at 0 degrees C. It will, given a good excuse, like a nucleation site or a surface to start crystallizing on. But if it's pure and not in contact with anything, it can get down to about -40 before it actually forms a solid. But if it's below 0, we call it supercooled, and it behaves, if it hits a surface, a cold enough surface, it will freeze almost instantly. If you go higher in the atmosphere, because you're now getting much colder, it's sufficiently cold for the water to actually crystallize. And sometimes it will sublime from water vapor, it will form crystals of ice. So a cirrus cloud, and contrails or ice crystals, they're tiny particles of ice, they're not actually liquid. Whereas much of the cloud, cumulus clouds you look at outside, when there are any, it's usually water droplets. And if it's high enough and cold enough, they'll be super cooled and you get freezing top. Now, what do these different types of cold water or solid water do to engines? So you might recognize the sort of partial GA of a Trent, top right. What we find is the supercooled water, when it hits the front of the engine components need to be cooler than about 10 degrees Celsius. If they're warmer than that, there's enough thermal energy in the metal to keep the water, to stop it freezing and actually make it remain as water, but it will be above 0. If you've got, it's a rule of thumb, it's not that precise, but it's about right. If the metal is less than 10 degrees Celsius, the water will pretty much freeze on contact. So you build up ice, and it'll do it around the front of the engine where the metal is cool enough. Now, it then can cause problems. We'll come back to the damage it does in a moment. Ice crystals, they don't actually form a problem predominantly in the front end of the engine. You need to get deep into the engine before they become a problem. And I'll illustrate how that works shortly. But you can still damage aerofoils. So this is actually some IP compressed aerofoils that have been bent by ice forming from ice crystals. The mechanical damage is one thing, but it also can cause operability issues. But let's look a bit more detail about the ice that builds up from supercooled water. So remember, this is water coming in at below 0. It only really can build up significant amounts if the engine's at low power. So idle, descent idle, some holding patterns, or on the ground taxiing. So freezing fog's a problem because the engine's at low power. If you raise the engine power, the front end of the engine gets warmer, so the ice can't form. And particularly on rotor blades like fans, the CF loading is sufficiently large that the ice will just get flung off. So you need to be at low power, and you'll get these icing patterns. There's an interesting one about the rubber bung at the front of on the spinner on the Rolls-Royce engines. We say the ice won't form on it because it breaks off. Actually, the ice forms wonderfully well on it. It does work as a anti-icing agent device, but it's the ice behind it that breaks off because it wobbles around. It breaks the ice off behind. And if you think about it, the ice forming at the center of rotation has got virtually no kinetic energy. The higher the radius, the more kinetic energy. It's more problematic. You get the ice building up on the fan blades. The problem is, and in the core inlet on the engine section stators and potentially aerofoils downstream of there, not off on the rotors, but occasionally get it on a rotor. But the problem really starts not when the ice is building up, but when it falls off. Because it can fall off with a huge amount of energy, particularly on a fan blade. It can go radially out and smash into the liners. It doesn't really go actually backwards. There isn't enough forcing on that, but the CF loading on those fan blades is enormous, and it slingshots the ice out, and you can damage your impact liners and acoustic panels. When it gets into the core, it's like throwing a snowball at 400 meters per second. It's going to hurt, and it will bend titanium and actually potentially break it. We're finding increasingly the problems are the sudden release of ice that then becomes water into the HP compressor, which upsets the aerodynamics, and you can get a surge and a flame out. And it usually happens when the engine's accelerating. So you build up the ice during descent idle or ground freezing fog where you're taxiing out. As you take off and accelerate the engine, the ice falls off into very fast moving turbo machinery with an HP compressor for which operability margins are minimized, and you get a surge and a bent rotor blade. The way to design your way out of that is to make your compressor blades thicker, so they're mechanically more able to deal with the impact. That comes at a weight and performance penalty, but you have to live with that. As far as wet operability, the only thing we can really do is to open bleed valves. That is expensive, but if you're only doing it during the engine acceleration up to power, that's tolerable. Ice crystals then. They're not snowflakes. The graphic on the left there, they come in all sorts of shapes, dumbbells, cylinders, odd sort of almost snowflake shaped things. I'm going to do a little graphic here. What look like bits of chocolate and baked bean tins are not to scale. They're just to represent ice crystals. You will only really encounter these, and they're certainly only problematic when you encounter them at cruise altitudes above 24,000 feet, which the front of the engine is cold, so the metal is usually below zero. So the ice crystals will not hit warm metal. They will just they will bounce off or break. The ones that go down the bypass duct, we don't worry about. There's not much equipment in the bypass duct that they can cause a problem. There's one or two, but they're fairly exotic and we can deal with it. We have had on the RB211s, 535 E4s, and some of the early Trent, there was a fairing on the spinner which could have an asymmetric gap. One section can be opening up, and you get the ice crystals forming in that location, and you get an out of balance and a high vibration. Flight crew, the cockpit flight vibration units are really high. The flight crew, it's vibrating so much the flight crew cannot actually focus on the instruments, so they naturally will think, oh, what's going on? Throttle back to idle, descend, go into warmer air, the ice melts, the problem goes away. Think, oh, what was that? The evidence is gone, but we figured out what it was. You can design your way out of that by designing a spinner fairing that, or a spinner that doesn't have a fairing. The really problematic stuff is when these ice crystals get into the core, get into inside the first stage of a compressor. For a Trent, it's the IP, where the air's warmer and you start to melt the ice, and you'll get a mix of ice and water slush, and around about 5 to 15% water, sufficiently wet for the ice for the slush to stick on a stator. If it's any more wet, it gets washed away. If it's any less water, it won't stick. So you start to build up, and because of evaporation, the slush refreezes to form a block. You can, I don't know if you know, you can freeze water at the ground in about +3 or 4 degrees C, because the evaporation effect will cool the water down to zero where it freezes, which is one of the reasons why in your car the warning light comes on about 4 or 5 degrees, because you can actually get ice forming when the ambient air is at 5. The interesting thing about being at altitude, and we've got time to explain thermodynamics, but it's to do with air density. That depression, we call it a wet, it's based on a thing called a wet bulb depression. You might have heard of wet bulb, dry bulb. So the wet bulb depression typically near the ground is about 4 Kelvin. At 38,000 feet, it can be 50 Kelvin. So you can have water at around 40, 50 Celsius because of the low air pressure, it can freeze. It's got, the temperature's got to get down to 0, but there's enough evaporative effect, because humidity is very low, you can do it and the water will freeze. So in our engines, we know the Trent's at plus 11, we believe the ice is formed. GE have had engines where at plus 34, they've had ice forming. But it forms deep within the compressor and you get these big lumps of ice, and when it falls off, you can bend blade, but the ice forms. This is based on a Genex, I think, but it's a 2-shaft with a booster. You get ice building up the back end of the booster, you get it in the swan neck duct, and you can even get ice forming at the inlet to the HP compressor. And the aerofoils there are not designed to take impact. They shouldn't see soft body impact. So when they get hit with a lump of ice, they can break. Those pictures are from a Genex on a B747-8. You also get the problem with supercooled water that you release a big, well, it doesn't have to be that big, but a sudden release of water. Arthur Rowe once calculated there's enough water in a can of Coke to cause the engine to surge. Not a huge amount. You can surge the HP compressor, flame can go out. It's a problem. And we have had problems with recent Trents where both engines are surged round about the same time. The dual engine surge at 38,000 feet isn't clever, but fortunately the engines do recover pretty quickly within a millisecond or a few seconds. Often the flight crew don't even know they've had a surge. Anyway, just to finish the story on the water threat, rain and hail, they basically drown the engine. You can ingest so much water that you can contract the IP casing onto the rotors and get a heavy rub that can cause a surge, or you can actually reduce the T3 or T30 so much that the flame goes out. This is about the only threat where it's the amount, not how long you're in it. Ice crystal, supercooled water icing, you've got to be in it for about of the order of 10 minutes before you can build up enough ice to have a problem. It's the amount of water in rain and hail that is the problem. We do testing. We used to do hail gun tests in Derby. I think the Trent 700 was the last time we did a hail gun. We substituted that with an equivalent test with water, but now as we go to the ultrafan, we're going to have to go back to hail gun testing because we have no reference point to work out what the equivalent water test is. Quite exciting test, but we're going to get back to them. Anyway, so that was a quick canter through the water threats. Now on to where the geology comes in, which became an interest of mine in 2010. Again, suddenly geology became interesting. So what are they? We call them the non-aqueous threats because they're not water. So we've talked about this mineral dust to give it its technical scientific term. You've got volcanic ash. You might think, well, it's 15 years since the volcano in Iceland, which I'll try and pronounce, Eyjafjallajökull. It's not quite right, but it's better than most people can attempt. That's actually Pinatubo, which was in the Philippines in '91. But I think at any one time, typically around half a dozen volcanoes are erupting, putting ash into the air, where they're having to issue advisories. The ash frequently doesn't get above about 10 to 15,000 feet. So it's only local air traffic that have a problem. But about 3 or 4 times a year, there'll be a sufficiently big eruption somewhere in the world that ash gets up to cruise altitudes, and that becomes more problematic. You've got to be in at those kind of concentrations. If you flew through that ash cloud, it wouldn't take long for the engines to stop. But at cruise altitudes, a bit further away from the volcano, the concentrations you need to be in several minutes, tens of minutes. So you've got to, the only time that's really going to affect you is at cruise. Volcanoes do put out a lot of sulfur dioxide gas, and that is a problem. It's not an immediate safety concern, but it can certainly damage your nickel alloys, the corrosion fatigue or sulfidation, as we used to refer to it, can degrade your nickel alloys and it can fail. Sulfate aerosols, so it's actually sulfuric acid, but tiny droplets of sulfuric acid, or nearer the ground, the sulfate aerosols we worry about are ammonium sulfate, but they're a source of sulfur. Again, that can cause corrosion fatigue problems. Sodium chloride, sea salt. You might think this is not a salty environment. We're almost 100 miles from the nearest sea. Can't get much further from the sea in England than Findon, I believe. This is a maritime environment. Heathrow is one of the saltiest airports in the world because the North Atlantic, and where we are this side of the Atlantic, because of the Gulf Stream and where it behaves, there's a lot of salt in the air, and Gatwick is also very salty. Auckland's particularly bad as well. So there's a fair amount of sodium getting into the engines down on the test boats down there that comes from either, depending on the wind direction, the Irish Sea or the North Sea. It's worse at Skegness or Llandudno, but you get the picture. Increasingly black and brown carbon, so soot or actually tiny oil droplets, they muck up your compressors and you lose efficiency because it's a dirty surface and the aerodynamic efficiency degraded. And there's a whole host of things that I regularly get asked about under the title Exotica, so wildfire smoke. It doesn't cause engines a problem, by the way, but people regularly ask. We've had insects, tree sap, tree sap above the Amazon at cruise altitudes. The convection is sufficiently high that you can get the sap from the trees getting up to cruise altitudes. It just mucks up the front of your engine. It doesn't really cause a problem. You just get an oily dirt. Anyway, so that's what they are. What do they do to engines? I'll talk about mineral dust and volcanic ash in one go, and I'll explain there are differences, but they're actually very similar. Front end of the engine, you get big erosion. These are hard particles that when they hit titanium or even nickel alloys at high velocity, they will take bits out. So you can get an erosion effect, and it's not just the rotors, the stator vanes can also get eroded, usually at the trailing edge and the tip. The pennies on the variables also get contaminated, and you can get frettage of those and they can start to not quite work well enough. But it gets really exciting when you get into the hot section, so the combustor and the turbines. And then modern engines are sufficiently hot that you will actually melt the mineral dust and the volcanic ash, and as a result, the particles will, when they strike a surface, a combustor tile, HP nozzle guide vane, HP blade, it'll stick. It forms effectively molten rock or magma, and builds up gradually, and that causes a number of problems. The one that's got the sand deposit in brownout conditions, that's a V22 engine or Rolls-Royce AE1107 engine. There's so much, that's an HP nozzle guide vane, there's so much deposit there, although you've not completely blocked the passage, they lose about 10% of flow capacity. That's enough to shift the working line in the HP compressor above the surge line, and you lose operability margins. That's the dramatic effect. Slightly more, I would say, acute damage is typically experienced in the deserts around the Persian Gulf, but it's now occurring in North India, North Africa, and other part in Northeast Asia too. You get these deposits. They degrade your aerodynamic performance a bit, not enough to stop the engine, but you're burning more fuel. But it drives a number of other problems. It can disrupt the effectiveness of your cooling films on the outside, partially block your filming holes, so the components run hot and therefore their life's degraded. You can also get degradation of, we now use ceramic, zirconia-based ceramic thermal barrier coatings to protect the metal. So zirconia it's a pretty robust, zirconium oxide is a pretty robust material. The volcanologists use it to scoop out the, when they're at a lava lake, there's a big, a crater full of bubbling lava, they will use a zirconia crucible to get the stuff out because it's pretty tolerant. Actually, if you get it hot enough and the composition of the sea mass, which has a calcium, magnesium, aluminosilica, it's a molten rock, but it's rich in calcium and magnesium, even that will dissolve zirconia. And when it either partially dissolves or fully dissolves the granite. It damages the thermal barrier coating, which then comes off. You've got bare nickel underneath, and therefore the component runs too hot and its life is degraded, and eventually it will fail. And that's the CMUS damage of thermal barrier coating. But if anyone if Rolls-Royce at the moment, everyone's talking, well, a lot of people are talking about CMAS, but that's what it is. It's a aluminum silicate with a lot of calcium and magnesium in it. You also get dust into the secondary air system. It finds its way all the way through the engine, and it will block up cooling systems internally. GE and Pratt & Whitney at the moment have got big problems with internal blockage in desert environments. They've found a way to the moment, the weak point in the Rolls-Royce Trent engines, and it's now affecting other smaller engines we make, is the CMAS damage to TBCs. GE and Pratt & Whitney have found a way to, I would say, partially mitigate that damage, but as a result, they're now using very fine detail cooling systems which are prone to blockage internally. So they're getting reduced life through the internal cooling passages are getting blocked. And I mentioned it a while back. The corrosion fatigue, you need the calcium and magnesium, calcium and sodium that comes in, and it combines with sulfur dioxide gas, and you get sulfate that corrode the nickel, and it fails. But let's just go back to what is the similarity or difference between mineral dust and volcanic ash. The two cartoon graphs maps of the world I've put there illustrate that geographically they occur in different locations. Not too surprisingly, the dust belt through the middle of the planet across North Africa, Central Asia, even into East Asia, is where you get very high dust. The Sahara Desert, Arabian Desert, the Central Asian Desert. And the dust from those does blow across oceans. So although Barbados is not a particularly dusty island, if you go 4,000 to 5,000 feet vertically up, there's often a band of quite heavy contaminated air, contaminated with dust, and it's from the Sahara. So if you take off and climb, as you take off and climb out of Bridgetown in Barbados, the engine's doing just quite a lot of dust, but it's not on the ground, it's in the air. The geographic location of volcanoes, well, the Pacific Ring of Fire is often known to many people. Yeah, there's a lot of volcanoes around there that have other locations. But what you find is near the equator, so I think Indonesia is the most volcano-dense country in the world, just ahead of Iceland. There's a lot of eruptions. There's usually 3 or 4 volcanoes in Indonesia that are erupting. But because of the stability of the air near the equator, it's very damp, very warm, the volcano erupts, the ash cloud goes immediately very high, like a cumulonimbus cloud, but then collapses and falls back down on itself. If you get an eruption at the high latitudes, either in the North Pacific, Europe, but down in South America, Chile and Argentina, mainly in Chile, those eruptions will get caught by the jet streams and dragged around the world. So actually, they are more problematic than the volcanoes of Indonesia. It's not good to fly in a volcano in Indonesia, as British Airways BA 982 found out, but actually there's more damage and more incidents that are associated with these high latitude volcanoes because the plume spreads out. So that's one difference. So I'm looking at the geology of mineral dust. So there's a photograph of a desert with dust. It's the dust in the air. It's not the dust or sand on the ground that's the problem. The engines, particularly in a civil airport where you've got a prepared runway, tarmac, there's not much dust on it. So the engines won't suck dust off the runway. People thought that's what the problem was. No, it's the dust in the air. And people. So how does the dust get there? Well, it's wind. There's obviously sediment on the ground, dry soil, very dry, and the wind lifts it off the ground and elevates it, and it can get it up to about 15 to 20,000 feet. But what we're really interested in is the composition of that dust. Now, the mountains around the desert or the bedrock are made up of these kind of rocks. I can imagine you've heard of them: limestone, sandstone, granite. There's plenty of others. The geology I remember as a young person in my teens and very early 20s was that a rock like granite is made up of a number of different types of mineral. So the mottled pattern on granite is because there's the 3 main mineral groups: quartz, feldspars and micas. You've heard of quartz, you've probably heard of micas, you may not have heard of feldspars. They're all aluminosilicates. So the white in the granite is quartz, the pink is the feldspar, and the slightly darker grey is the micas. But when you break that piece of rock up into smaller and smaller bits, and you get below a millimetre, and it becomes dust at about 1/10 of a millimetre, it's not granite anymore. It's fragments of quartz, feldspar, and mica. The same is true for limestone. It's predominantly made up of calcite and dolomite. Dolomite is magnesium calcium carbonate, with calcite is calcium carbonate. Same with sandstones. They get broken up. Feldspars are not very stable in the atmosphere. Left long enough with a bit of water and time, they form clays, and we're all familiar with clays. But that is what the dust in the air is made up of. Tiny fragments of these minerals. There are a few others, and we'll talk a bit more about them in a minute. It isn't being tiny bits of rock. So the dust is a cocktail of quite a wide range of different minerals, aluminosilicate minerals, carbonate minerals, sulfate minerals, and occasionally sodium chloride. The composition of the dust varies depending on where you are on the planet, and that shouldn't be too surprising to a geologist, and in fact it isn't, because that's the Arabian Peninsula. The rock that makes up the Earth's crust in those locations is made up of a whole variety of sandstones, limestones, granites, metamorphic rocks that are ancient, 3 billion years old, that kind of stuff. That all gets weathered, broken up, and elevated into the air. And you look at volcanoes, very dramatic, very exciting to young people. Kids love them. But they're broad. There are other classes, but the extremes, you get explosive eruptions and you get effusive eruptions. There's a volcano that's been erupting on and off in Iceland for about 3 years now, but that's like the bottom one. It's an effusive eruption. It's oozing lava out and a fair amount of sulfur. That's not a problem to aviation. It's the big explosive ones, and they put a lot of particulates high into the atmosphere. The science that you need to understand the threat is really the technology behind satellite detection of these ash clouds, where they are, but also mathematical modeling. They basically do CFD models of the atmosphere, seed it with what they believe is the quantity and altitude of the ash, and model where it goes. And the places that are really, the UK is very good at this sort of stuff. The US, the Australians, the Argentinians are good at it too. But we work pretty closely with these universities and the Met Office. So we're very lucky here that we've got access to a lot of expertise, but you need to know how much and where it is to really understand this problem. So that's the science. But let's look at, does it matter as far as the engine's concerned? Well, people in 2010, their big concern was volcanic ash is really dangerous. We've had engines fail in volcanic ash, but we've not had engines fail really in mineral dust in desert environments. So why would ash be more problematic than desert dust? Well, I've already mentioned this. Volcanic ash is essentially aluminosilicates, but that is also true of mineral dust, although there are carbonates and sulfates. So chemically, they're not that different, but the actual material structure is, because volcanic ash forms from a liquid, very hot, but liquid rock that then cools very quickly, silicates take a long time to crystallize properly. And if you chill them at a reasonable rate, and I'm talking minutes to hours rather than years, it forms a glass. A glass is an amorphous solid that has a different melting characteristic to a crystalline material like ice or quartz. Not only does it have a different melting behavior, it tends to melt or go sticky at lower temperatures to a dust like quartz or feldspars. And often if it's a pumice, and there's a lot of gas expelled as the volcano erupts, it can be much more abrasive. It's like glass paper as opposed to a crystalline material. That was the perception after 2010. But actually many people in the military, and we became aware of this, actually if you look at real world dust like you get in the Persian Gulf, they can melt because they've got volatile constituents like clays, the carbonates and sodium chloride. They can melt at temperatures of similar range to volcanic ash. In terms of the abrasive nature, there isn't a lot of difference either. If you break up a rounded quartz fragment and compress it, it gets pretty abrasive as well. Given a choice, I'd rather operate in mineral dust, not volcanic ash, but they're actually both pretty damaging. So what is the difference? Why do people worry about volcanic ash? Well, there is a reason, but many people didn't realize what it was, and that's explained by this chart. A plot of concentration along the x-axis as a log scale in milligrams per cubic meter. The vertical or y-axis is altitude, either in meters or feet. You'll see that I've used a log near the ground, log scale in meters, and then it goes linear from about 3,000 meters, or what is it on the other side, 10,000 feet. And there's a reason. I want to resolve what goes on near the ground. Now, that range of concentrations and that range of altitudes from the surface right up into the troposphere, into the stratosphere, you can find volcanic ash in any combination of those. To get very high concentrations, you need to be in the eruption plume. But the key thing about that is the eruption plume can go all the way through the troposphere into the stratosphere. If you look at, and there's some pictures that illustrate those phenomena. If you look at mineral dust, because it's only elevated into the air by the action of wind on the ground, it's limited, one, the concentration you can get to, and two, how high it gets. It gets quite high. It's surprisingly high to a lot of people. But even if you get a biblical sandstorm, like a 1 in 100-year sandstorm, although they're occurring every 10 years now, but you might get up to 10 milligrams per cubic meter, maybe 30 milligrams per cubic meter near the ground, but it attenuates fairly rapidly. And this, for me, is the key difference between volcanic ash and mineral dust. Naturally occurring mineral dust, and I think there's some photographs here to illustrate that, it's limited in the concentration it can achieve, or you can expose yourself to. At cruise altitude, you can get mineral dust, but you need a convection system like one of these in the photograph there. Aviators will avoid them, not because they might contain mineral dust, because they contain a lot of horrible things like high turbulence, a lot of water, ice crystals, things like that. It's not much of a problem. There is another class of mineral dust occurrence in the atmosphere, and that's what we call aircraft generated, and that's when you've got a helicopter or a tilt rotor in Brownlow condition. They will produce concentrations of sand, similar concentrations you get in the plume of a volcanic eruption. Now, what's interesting is if you plot events on this chart where we've known that there's been a safety implication or cost of ownership implication. So my color scheme is red for safety, yellow, not good, you've damaged the engine, but it's still usable, but it's an economic impact. You'll pay long term, you have to pay. It'll use a bit more fuel than you'd intended, and you might have to bring it in for overhaul a bit earlier, 100 flights or so. That's an economic cost. And then differentiate between volcanic ash as a solid color and mineral dust as the checked coloring. The ellipses I use to illustrate the level of uncertainty. I could use error bars, but they tend not to be that visible. Ellipses are much better. So on this chart, the vertical axis of the ellipse is the uncertainty in the altitude, the horizontal axis is the uncertainty in the concentration. And you can plot on there events where they've had safety implications and where they've only had economic damage. People could say, oh, you just cherry picked those. You've picked the safe to the right, the safety ones, and to the left, the economic damage. But you'll see in the next chart, there are no red ones to the left of a line roughly there. There are yellow ones to the right of it, but that's because they weren't in it very long. And that, to me, is the big difference between volcanic ash and mineral dust. It's not the nature of the materials, it's how they present in the atmosphere. Volcanoes can put very high concentrations, problematically high concentrations at cruise altitudes. Mineral dust, that won't happen. Yeah. So this is the bit where I was very fortunate in getting a lot of recognition and got to meet the King's sister as a result. Nice event. But it's the work I did on volcanic ash. And this chart, the Americans call it the Clarkson chart. I'm too modest to tell you that. I refer to it as the DVAC chart, the duration of exposure against atmospheric concentration chart. So it's the concentration range along the x-axis again, but the y-axis is now how long you're in that level of ash or mineral dust in hours. So 1 is 1 hour, 0.1 is 6 minutes. And these 29 events, and again, the ellipses indicate the level of uncertainty in the concentration or how long they're in it. The check colouring is relevant mineral dust, not all mineral dust. Some mineral dusts don't compare well with volcanic ash at all, but these ones do. They're rich in the carbonates and the sulfates and things like that. You can see there are patterns there, but we built a mathematical model, relatively simple in what it represents. Many people get scared by that mathematical equation. It's an ordinary differential equation. Certain circumstances you can integrate it analytically, but from the more general case you'd use a numeric approach. And if you work out the limit of safety by varying concentration and time, you get a reverse S shape like this. And it's because of the balance between the rate at which the ash is building up, but it spontaneously falls off. This happens with mineral dust as well. You can clean an engine up by running it in clean air for long enough. The deposit actually comes away in little bits. So we've got a representation of both. The bottom right of this chart, the deposition dominates. It swamps everything. And you swamp the aerofoil, big deposit of ash builds up and you lose your operability margin. To the left, you get more of the deposition to the point at which deposition actually becomes as big as the shedding becomes as the same magnitude as deposition. And the turning of the curve at the top towards the top of the chart there is to do with other failure mechanisms coming, like erosion and compression. To illustrate why there's such a big gap or interval between the two red lines there, the pink region and the red, is because for this illustrates for a given engine type, it's actually based on the Trent 7000, you vary the degree of degradation of the engine, how old it is it brand new or about to come in for an overhaul, and you change the type of ash, the composition of the ash, and ash in varied compositions, you can get different lines here. So there's a lot of, for a given, if you've got a brand new pair of engines in a relatively benign ash, you can operate for quite a long time compared to a set of old engines in a really, the worst ash is a thing called basaltic ash that's very high in glass. That information and that understanding allowed us to define a region in this chart, bottom left, where you can operate in ash, but you're not going to end up with a safety problem. Anyway, moving on, conscious of time. I've mentioned most of these, if not all of them. You can categorize their impact in terms of the safety implication or the cost of ownership. They're the two impacts that we're really worried about. The safety implications requirements or definitions are set by the regulators, the FAA, the EASA are the two main ones, but there are others. When it comes to cost of ownership, and you've noticed I've got the aviation stakeholders, so the airlines, the engine manufacturer, the airframer, and the regulator. When it comes to cost of ownership, because of the way we do total care contracts, it's only really the engine manufacturer, or in our case Rolls-Royce, that really worries about it. The operators don't like it, but you'll see that slide coming up that most of the liabilities are on Rolls-Royce. The airframers worried because if the engines are no good in the desert, their reputation suffers, they can't sell their airframe. But the cost of repairing or maintaining the engines is down to Rolls-Royce. Whether it be safety or cost of ownership, the approach EEP uses to try and assess the impact of these is to calculate the rate of damage or the degree of damage. We attempt to improve the design, either retrofitting or making changes that engines are in service, or when you design a new engine, try and get the chief design engineer to allow for the fact there's a real environment out there. But increasingly, we're looking at recovering costs through cleverer service contracts. Now, there's another approach we developed as well to break down the problem, which is to break it up into three elements. So there's a wireframe of a two-shaft engine. The first thing is to understand the nature of the contaminant in the atmosphere, so what it is, where it is, and how much it is. And once you've got that, you can work out when it comes into the engine and how much gets into the engine. And from there, you can start to figure out what happens to it in the engine. So element two is what happens. So you've worked out how much comes in. Now you've got to work out what happens to it. So in ice crystals, it's got to melt and refreeze. Mineral dust, you'll see in a minute, it can undergo a number of changes before it actually gets to a damaged site. Once you've done all that, then you can start to work out the actual rate of damage, be it corrosion effect or a cooling system blockage effect. Now, to illustrate that, take the water threats. There's a lot of complexity about understanding the nature of the water threats in the atmosphere, like altitude the water gets to, how much the rate frequency at which you get freezing fog conditions, where on the planet you get high ice crystal conditions, and it's usually between the tropics where the air's sufficiently warm, you can get a lot of water high. Most of that's defined by the regulators or pretty well understood science, although that's still improving. The challenge comes to how you model the impact on the engine. And we're only really just beginning to do that. And then you can start to advise the compressor blade designers how to design their compressor blades to withstand it. When it comes to mineral dust, although we've got a reasonable understanding of its nature in the atmosphere, it's certainly better than we had 10 years ago, there's still an awful lot we don't know. We do have found out in recent years that when mineral dust comes in the front of the engine, it undergoes, and the two key changes are its particle size distribution goes from relatively coarse to much, much finer, and that changes the way it behaves and where it can get to. But we've also found out that the composition changes because it undergoes very rapid heating. Some of the minerals break down and form new minerals. It's basically metamorphic rock formation, but not on geological timescales. This is all happening in milliseconds or fractions of seconds. In geology, it takes millions of years. This is why the geologists get really excited about this. The only natural phenomena the way you get these heating rates are when an asteroid hits, and that doesn't happen too often. We do computational analysis ranging from very simple models. That chart on volcanic ash is a handy way of assessing the impact, right through to very complex 3D, 4D computational models. And we do intermediate models as well. We do a lot of testing, very expensive. The far right is an ice crystal test at NASA Glenn in Cleveland. One of those tests, we haven't done it yet, but the cost is coming out around 30 to 40 million pounds. Not cheap. The ones in the middle are typically 4 to 5 million. Not cheap, but the company's prepared to pay for those. But we're also finding getting lots of data from in-service engines is very useful. Poor quality data, but it's a lot of it is still very useful. So we use those techniques. I mentioned total care contracts. This panel is taken from some marketing material the company used 4 or 5 years ago. And I've circled in red the bit that is fascinating. We were advertising to the airlines, take up a total care contract because you're fully transferring your financial risk to Rolls-Royce, which is a bit short-sighted, Rolls-Royce, because if they operate in the deserts, which some of the big operators do, the engines degrade, we're going to have to pay for the cost. They did try and mitigate that by putting a clause in that said if you operate your engines in abnormally erosive or corrosive environments, you're paying. But their clever lawyers said, well, define what you mean by abnormally erosive and corrosive. And we thought, that's very subjective. We then had to go, not me, somebody else had to go to say, well, it'll be abnormal as defined by the airworthiness authorities. But then, well, who are they? You might think you know who they are. EASA don't call themselves an airworthiness authority. They're a certification agency. The CAA are not an airworthiness authority. They're an aviation authority. So it's not, what do you mean by that? One thing we started to do as a company about 15 years ago, and again, before I got involved, defining airports where we thought there was a lot of sand and the engines would degrade. It wasn't Justin Stadium, was it? Jason Stadium. But that was a picture that illustrated it. We got our field officers to look out their office windows and say, is it sandy outside? And these are the airports where they said it was. Actually, Alice Springs and Las Vegas are not very sandy. We said that's terrible. We actually, after a lot of lobbying and arguing, got some science data and from the atmospheric science community. We said, actually, if you ignore Alice Springs and Las Vegas and you take the most benign of the 50 remaining, any airport worse than that, we'd include on the list. It came out at 276. And you can see a lot of Asia, Central Asia, and even the Caribbean came in. They've now implemented this, and they reckon it's saving the company hundreds of millions, if not billions, in improved revenue. A few more slides. I'll whiz through it, and then we'll get to questions. There are again, from the initial assessment 15 years ago that it was just sand at the airport, we said, well, it's not, it's sand, not just at the airport, but on the flight route. And this was some work done at Reading University a couple of 3 or 4 years ago, where they said, well, actually, you might think Delhi is a relatively dust-free city, but in the middle of the year, this time of year, the dust levels and the vertical axis of altitude, it's worse than Doha or Niamey in Niger in the desert. Phoenix, you might think it's in a desert. You might think it's dusty, but actually the dust levels there are an order of magnitude smaller than places like Delhi, Doha, and Niamey, and Abu Dhabi and places. It's not just the quantity of dust. I said we come back to this. Composition matters a lot. Delhi and Dubai or Doha, they're similar. The dust levels are similar, but if you look at the composition of dust in Delhi, it's relatively benign because it's mainly quartz and feldspars with a few clays, whereas the dust in Abu Dhabi, Doha, Dubai, they've got a lot of calcite, dolomite, and gypsum, which are full of calcium and magnesium. Big problem for CMUS damage, and that's why we're seeing CMUS damage in that region. We do see it in Delhi, but not at the same rate. Beijing is similar to Delhi. We have tried to map out where you're going to get the really damaging minerals. We thought the soil maps would be useful, but the scientist says actually they're not. What you really need is a bespoke database, and we got Manchester to look at sources of information. So we've got a better understanding of the composition of mineral dust on the ground. We need to convert that to dust in the air and always through this. So this is my final slide. So some final thoughts as I'm 2.5 weeks from retirement, but I'm not disappearing. I'm going to be this in a minute. I've got a plan. Working in engine environmental protection is interesting. You do stuff that other engineers wouldn't do. It might look a bit sciencey and complicated, but actually, if you spend a bit of time, you can get your head around it. Most of the geology and chemistry I've talked about here, you would cover at school. It would be school level, not degree level. Rolls-Royce has realised you need it. We do collaborative work with Pratt & Whitney at Virginia Tech. GE never like to talk to anybody about what they're doing, but you can figure out what they're doing from media press releases. They are beginning to realise they need to have this kind of capability as well. They need to get access to geologists and meteorologists and people like that. We do get involved in some really quite cool, exciting, well, cool because they're icing tests, but quite exciting tests, putting dust and water into engines. We do, personally, I've had a terrific 15 years traveling, not all the time, some of the time going to exotic locations like Buenos Aires and Wellington and Tokyo to talk to scientists about atmospheric phenomena and what it does to engines. This is tongue in cheek. Chief engineers do like to design beautifully fuel efficient, cost efficient, weight efficient engines, and then we say, yeah, but it won't survive, and they have to modify it. It's actually quite a painful experience because the original Ultrafan, I think they worked out that compared to the last strength XWB, was 20% more fuel efficient. But by the time we'd had a go at it, it said, but you'll need that, that's no good. That drops below 10% later. You can lose an awful lot of fuel efficiency by designing it designing it badly for the environment. And where for me next? Well, I did say at the beginning I started off as a geologist. As I retire, the company are going to pay for me about 1 day a week to be a geologist at Manchester, which is quite funny because I'm not a geologist, but it'll be fun for a while. Anyway, thank you very much.